and then so dear
Whatever
colleagues,
works.
dear colleagues, dear participants, we are opening the first seminar in the new year. Uh, it's a great pleasure to introduce our today's speaker, Aephraim Steinberg. He's a professor at the University of Toronto and founding member of the Center for Quantum Information and Quantum Control. His research addresses open questions in fundamental quantum mechanical concepts and historic experiments such as mapping trajectories of photons passing through a double slit via weak measurement or timing particles tunneling through a barrier. He completed an undergraduate degree at Yale University, then attended the University of California at Berkeley for his master's and doctorate. His 1994 thesis was entitled When Can Light Go Faster Than Light? The Tunneling Time and its Sub-Femtosecond Measurement via Quantum Interference. And it received an award from the American Physical Society. The publications containing the main results of his research have been cited extensively and reached a wide audience through popular science publications like Scientific American and Physics Today. In particular, in 2011, Steinberg was awarded first place by Physics World in its early top 10 breakthroughs for his work on mapping trajectories of photons. Professor Steinberg enjoys encouraging physicists to embrace new perspectives, including asking so-called forbidden questions. For his scientific achievements and popularization of science, he has received a number of distinctions, awards, and honors. And his today's lecture is entitled, What Did You Do Last Nanosecond? Experimentally asking photons and atoms about their past. So with this, with pleasure, I'm passing the microphone to Professor Steinberg. Please, the floor is yours.
Well, thank you very much for the kind introduction, and thank you all for the invitation and for being here, especially at a somewhat later hour than usual. And I just want to express our respect for you guys trying to keep science going and keep these activities under the situation that you're in now. And your, everyone's thoughts in Canada are with you. With that, let me shift to telling you about some science and indeed things that might seem like forbidden questions, asking what happened in the past in quantum mechanics. And you reminded me, Andre, asking questions that I've been asking for 30 years that I thought that we had moved past, but they keep coming back and getting to us again. So there's a picture of our campus, the view from my office, not in this season, but when the weather is a little bit warmer. And what I'd really like to do is just begin by giving credit to the people who really did the work I'm going to be telling you about now. I'll try to mention some of the names as we go on, but it's really a heroic group of people that we've had here. I'm going to tell you mostly about two different experiments from our group, and I've tried to highlight the most important contributors to those works in red. One work is on studying atoms tunneling through a barrier made of light. And it was many generations of students, beginning with Anna Joffrey, Chris Eleanor, Mirko Zirka, who really built that up. But it was Shreyas Potnis and Ramon Ramos who really brought that experiment to the state that let us do what we'd been talking about for over a decade. And the most recent work was by David Spearings and Joseph Magua and Nick Mantella. Joseph, who just successfully defended his PhD yesterday. On the other side, I'll talk about some experiments that started out as real quantum optics, nonlinear optics, the current iteration of which was really pioneered by Amir Fayezpour and Mateen Halaji, but then kind of shifted gears under Josiah Sinclair, who's just started a position as a professor at the University of Wisconsin. And those experiments have been picked up by Daniela Angulo-Murcio, Kyle Thompson, Vida Nixon, and Andy Zhao, and try to tell you about all of what we've been doing. I should also credit Howard Wiseman and Joseph Tywissen. Joseph is an experimental collaborator now, but was a theory contributor to some of our earlier work. And Howard has been a critical theory collaborator on many, many experiments over the years. I wanted to set the stage by explaining that one of the obsessions we have in my group has long been this business about asking about the past. And I think of this as a branch of the question of how to think about the wave function. Is the wave function really a description of what's out there or merely probabilistic? Could you imagine knowing more about a particle than what's in its wave function? And one way we think about that is to think of what I call quantum archaeology, the idea that a present observation of a dinosaur bone teaches us that there was some creature wandering this planet 65 million years ago. And meanwhile, in quantum mechanics, we're often taught that if we build, let's say, a two-slit interferometer and a photon reaches the screen, it's forbidden to ask which path did the photon take before it reached the screen. If we didn't measure that at the time, the question allegedly becomes meaningless. So in classical mechanics, one gets extra information about the past from present observations. And in quantum mechanics, we're often told that's not true. I think that doesn't make any sense. And the reason I think that is because most quantum physicists today believe that that dinosaur and that bone were actually following the laws of quantum mechanics. So when we dig up a fossil and reason about the past, when we measure the cosmic microwave background and we reason about the Big Bang, we are learning about the past of quantum systems. The issue is that there are limitations. The same way the uncertainty principle limits how much we can say about the future, there are limits on what we can say about the past. And there are perhaps different measurement strategies depending on what we want to learn. So these are the questions that really interest us. And what I'll do is I'll describe these two different experiments. First, I'll introduce the question of tunneling times. It's a 100-year-old question now, but not everyone has heard about it. It predates this business of retrodiction, just a very simple question. How much time does a particle spend in a forbidden region, a region it's not supposed to be in at all, before being transmitted? And I'll talk a little bit about what we hope to do over the next few years, which is to move beyond simply measuring that time and actually learn even more about the history of the atom, try to understand what is its trajectory, so to speak, as it traverses this barrier. And finally, a theory paper that we hope to submit very shortly and then follow up with experiment if we can, asks what the act of trying to observe a particle while it's in this region does. Can you change the nature of tunneling simply by looking for the particle? And those experiments were really aimed at this longstanding mystery of the tunneling time and at quantum retrodiction. Whereas we then picked up with another experiment, instead of looking at atoms in light, started looking at light in atoms. And originally, this wasn't where this was going. We kind of stumbled into this question and realized that we were basically asking, when a photon traverses an atom cloud, how much time does that photon spend trapped as an atomic excitation? And that proved to be a really surprising question. So here's the background to tunneling. I think we're all familiar with, but we all learn in university how to calculate the probability that a particle reaches the far side. And in most textbooks and most courses, we never even ask the question of how long it takes to get to the far side. Obviously, we can think about this semi-classically. If we have a barrier and a particle with energy above the barrier, that difference gives us the kinetic energy. We take the square root, that gives us a velocity, and we can calculate a time. As the energy drops towards the barrier height, the kinetic energy goes to zero, and that time would classically diverge. Even worse, if the energy is below the barrier, the internal kinetic energy is negative. And if you try a semi-classical approach, you get an imaginary velocity, an imaginary time, and we really don't know what to do with that. That's not to say that people don't know how to calculate these things. We know how to handle wave propagation. We can look for basically the group velocity or the group delay, typically using the method of stationary phase. And people have applied this to tunneling since the 1930s, and more famously with Wigner and Eisenbud's work in the 1950s. You don't hear about it that much, and my impression is that we don't hear about it because the results were so confusing that people weren't sure what to say about it. If you follow the stationary phase approach, then a problem arises. Stationary phase involves looking at the relative phase of different energy components as they traverse the barrier, looking at this transmission amplitude T written on the upper left-hand side, and typically phase is accumulated as you propagate. Except Inside a tunnel barrier, as you see in the upper left, instead of accumulating phase, you have a real exponential decay. The phase of the wave function essentially does not change across the barrier. And what that means is you can let a barrier get thicker and thicker and thicker. And to good approximation, the transmission phase does not care about that thickness, which means that anything you calculate from the transmission phase, like this group delay, also becomes independent of the thickness of the barrier. And this is something that's known as the Hartmann effect. It was pointed out in the 1960s, but it was implicit in this earlier work going back to 32 and 55. The problem here is that obviously you can imagine a barrier so thick that this time that's independent of d is less than d divided by c. So it seems to violate relativity, and that made people think there was something wrong here. Calculation could be wrong. The idea of an infinitely rigid barrier might be a bad approximation. Stationary phase could break down. Or finally, the Schrodinger equation is not a relativistic equation. Maybe it's just an artifact. The latter is not true. People quickly repeated the calculation with the Dirac equation, with Maxwell's equations, both fully relativistic, and found the same effect. So it has nothing to do with the non-relativistic nature of that equation. And of course, even if you want to doubt the stationary phase approximation, there are more sophisticated mathematical techniques. And for that matter, there's just direct calculation. And on the upper right, you see that these days, if you want to calculate it, all you have to do is go to Google or go to Wikipedia and download this movie that someone else simulated. If you measured precisely enough where that outgoing peak was, you could find that it appears in a time shorter than the time something traveling at the speed of light would take to traverse the barrier. So this confused a lot of people. It led us and other groups in the 1990s to measure the tunneling time for photons in particular and confirm that this group delay prediction was right. It turns out that if you go back to some work in the 1970s and 80s, there were a few groups that had already understood this, similar to understanding anomalous dispersion. And it turns out that there's no contribution with relativistic causality. A very, very small peak is transmitted. And the fact that the peak of that wave function appears faster than light does not mean that any energy has traveled faster than light, and does not mean that any information has traveled faster than light. And I won't dwell on that. I'd be happy to talk to people about it, but it's really quite well understood. It looks as though something has traveled faster than light, but in fact, there's no causal connection between the peak of the incident wave function and the peak of the outgoing wave function. It just happens that the way the wave functions get reshaped, that's how it looks. The question this leaves us with is, what is the time scale we should really think about the particle having spent in the barrier? Clearly, the peak is not an absolute location of a particle. It doesn't describe a real trajectory, and yet there should be some appropriate timescales for describing tunneling. And we'd like to be able to think about what the particle did as it traversed. In particular, this question got re-raised in the 1980s by a lot of condensed matter physicists. Marcus Buettger and Rolf Landauer were among those who really pursued it most assiduously. And they were concerned with understanding how to think about the real detailed condensed matter physics of, let's say, a tunnel diode or a squid or other devices that involve tunneling. And they started thinking in particular about what happens if you just look at one particle that is transmitted. And of course, when we draw these wave packets, they include a transmitted portion and a reflected portion. But at the end of the day, if you detect an electron, you might detect it on the far side of the barrier. And it's an interesting question to ask, how much time does just the transmitted particle spend in the barrier? After all, the reflected particle doesn't need to go through most of the barrier. You might think they'd have different histories. And in my mind, that's the underlying philosophical question. Can you separate the history, the behavior of just the reflected particles and just the transmitted particles? In the 80s, there were some authors saying that simply isn't a valid question. The entire wave packet describes every particle until the moment of collapse. I think that was a too simplistic picture. So as I said, Buettger and Landauer got very concerned about this question, And they decided to devise new thought experiments where basically particles could carry stopwatches. There'd be some way of really probing what is the time this transmitted particle over here feels like it's spent inside the barrier. And there are many, many different ways to do this. And I don't want to go through the history of all of these experiments, but I'm just putting up a slide here to indicate a few of the experiments that have been done. To my mind, the real pioneering one in this field was this 1989 paper in the upper right, done in Daniel Estev's group, by a group including John Martinez, Michel Devoré. Basically, this experiment and this squid pictured on the left over here are related to that last Nobel Prize and is the grandfather of today's superconducting qubits. But they did have this one series of papers really probing what is the timescale for the macroscopic tunneling in these devices. There were a lot of other experiments, as I said, looking at photons. It's often easier to do these foundations experiments with photons. They were a little bit indirect. And then more recently, over the last 15, or I guess now 17 years, Ursula Keller's group using attosecond ionization of rare gases, and also hydrogen more recently, has built what they call the Atto clock. And they generated a lot of controversy, although I kind of think the time they're measuring is best thought of as being related to this group delay, not really the time spent in the barrier, but the time of arrival of a wave packet peak. And there were a lot of atomic physics complications leading to a lot of controversy. There's also a 1999 paper on the lower right here using cold neutrons, which is really interesting and turns out to be very analogous to the work that we've done with neutral atoms that I'll tell you about now. So the way we want to do this is by trying to measure the time an atom spends in the barrier by probing it only while it's in the barrier region, but doing this without simply knocking the particle out of the barrier or giving it so much energy that we're no longer looking at tunneling at all. And that's something that's often referred to in the literature now as weak measurement due to a formalism by Yakir Aharonov and his collaborators. Really, what's interesting about these measurements is that since they don't disturb the particle, they allow you to post-select on where the particle is found later without having disturbed the evolution on the way. And the weakness is simply a necessary condition for being able to do that post-selection. It turns out that even before Aharonov and his buddies invented this formalism in 1988, 89, I guess 88, the same idea had appeared in a lot of work on tunneling. Oops, next slide. And in particular, Marcus Büdeker popularized what we call the Larmor time, which goes back to earlier work by Bas and Rybachenko, which basically said, if I have a particle with a spin, then that spin precesses whenever the particle sees a magnetic field. So if I'd like to probe how long a particle spends in this rectangular barrier, I could imagine spin polarizing the particles, let's say along the x direction, and confining a magnetic field along z only inside the barrier. This way, when the particle is outside the barrier, it freely propagates without its spin being changed, but while it's in the barrier, the spin will precess at the Larmor frequency around B. So if we look at a transmitted electron, and we measure the spin precession angle phi, divide by the Larmor frequency omega L, that will reveal a time scale that they interpreted as being the time spent in the barrier by this particle that was transmitted, right? You could imagine doing that measurement independently for transmitted or reflected electrons. Obviously, the magnetic field disturbs the evolution, right? That was clear to everyone from the beginning. So their proposal was to take the limit where the magnetic field is so weak that it has negligible disturbance on the transmission properties. And if this ratio remains well defined, we can still define a time without greatly disturbing the particle. So that's the basic idea here. And that's exactly what we decided to do. We decided to do it with atoms because we know how to make atoms tunnel now, although it took us 15 years to actually get there in the lab. And they have internal spins that we can manipulate. So let me describe our own system. We don't work with electrons. We're no longer working with photons. We work with rubidium-87, which has the nice property that it's relatively straightforward to Bose condense it, which means that you get essentially an atom laser. You get thousands or millions of atoms in one wave function with a relatively long coherence length. In fact, there are extra tricks there, but we managed to get a coherence length of about 4 microns. And that's exciting to us because we can make potentials for these atoms by using laser light. And laser light can be focused down to the order of the laser wavelength, which is more like 1 micron. So we can generate atom waves with a wavelength that's larger than the size of this entire barrier. So in particular, we condense the atoms in the intersection of two laser beams that form attractive potentials for the atoms, red detuned laser beams, also known as a dipole trap, or here a crossed dipole trap. But then we add a second beam that's blue detuned, which turns out to make a repulsive potential for the atoms that we focus down to 1 micron and we intersect with the trajectory of the atoms. We can adjust the height of the barrier just by playing with the intensity of the laser beam. And we actually have to lower that, the atoms are so cold, to about 150 nanokelvin, which is much, much more than the 1 nanokelvin temperature we're able to cool our atoms to. And it corresponds, in terms of kinetic energy, to a velocity of approximately 4 millimeters per second. So the idea now is if we push the atoms at 5 millimeters per second towards this laser beam, they'll sail right through. If we push them at 3 millimeters a second, they'll all be reflected. And if we push them at 4 millimeters per second, about half of them will tunnel through and the other half will be reflected. There's just a movie. It's from an earlier iteration. We were trying to use a vertical geometry for the experiment that didn't work very well for the tunneling we wanted to do, but it still just amazes me. Here we both condensed the atoms and we placed the barrier right under the atom cloud. So we were using gravity to pull the atoms through the laser beam. And what you see is that some atoms have high energies, they're very hot, and that first cloud just falls right down. But after that, the atoms are just sitting on a sheet of light that's about 1 micron thick, and they spread out and roll over the edges. But of course, there must all the time be some atoms tunneling through that barrier. And in early days, we weren't able to resolve that. That was a lot of the experimental work that Shreyas and Ramon and Roxanne Chang, whose name I left out earlier, contributed to, until eventually we could really see this tunneling. Now, we still need the Larmor clock. And one of the reasons we went to atoms is that personally, I don't know how to confine a magnetic field within the de Broglie wavelength of a particle. I imagined that people might be able to make some small cold system where electrons traveled ballistically and then tunneled through some region, a quantum dot or something else. But how to confine a magnetic field in that region, I don't know enough about it. I discovered belatedly that the neutrons people believe that they can make thin enough layers that they effectively have a magnetic field kind of interaction in a very thin region. For us, what we realized is that one way of coupling different spin states of atoms is not with a true magnetic field, but with laser beams. So what I've drawn on the right is the level structure for rubidium in the electronic ground state. And in the ground state, there are two different hyperfine levels, F equals 1 with its 3 Zeeman states, and F equals 2 with its 5 Zeeman states. And in particular, if you just focus in on the M equals 0 states, which are largely insensitive to outside magnetic fields, these are exactly the same states that are used, except in cesium, to define the second, right? This is how you build an atomic clock. You probe that very, very narrow transition. In cesium, it's at 9 gigahertz. In rubidium, 87, it's at 6.8 gigahertz. And we decided to use these two levels, F equals 1, M equals 0, which we call minus X, and F equals 2, M equals 0, which we call plus X, as our spin 1/2 system. Now, these can be coupled directly by microwaves, but of course, microwaves have a very long wavelength. I can't probe inside our 1 micron barrier with those. But you can also couple them by using a 2-photon transition. So a photon which excites you from this ground state manifold all the way up to the excited state, which is 400 terahertz above, an electron volt above, and a second laser beam which brings you back down, but has a difference frequency with the first laser of 6.8 gigahertz. So you come back down to the other state. And this is a coherent coupling. Mathematically, it's exactly equivalent to a magnetic coupling of two spin states, except the laser beams can be focused to on the order of a micron. So what we'd really like to do is have this rectangular barrier and focus the two Raman beams somewhere inside the barrier to probe how much time the atoms spend in that region. In practice, we focus our barrier beam as tightly as we can, and it's not a rectangle, it's a Gaussian, and it's about 1.2 microns across. And since that was the tightest focus we could make in our old apparatus, we can't make the Raman beams any smaller. Instead, we actually just modulate the barrier beam itself at 6.8 gigahertz and play some extra tricks because it turns out if we had two sidebands, that would cancel out the interesting effect. We need to isolate just one sideband. And the barrier and its own sideband now act as this Raman beam, as a magnetic field. So what that means is that the atoms that are trying to tunnel through this barrier, they precess between the minus X and plus X states only while they're inside the barrier. And we have exactly what Budeker wanted. If we put it all together, here's the sequence. We Bose-condensed atoms in this cross-dipole trap. We turn off one of those beams, so the atoms are now in a one-dimensional trap. We think of this as a kind of waveguide. It allows us to do one-dimensional physics. We cross that trap with our blue-detuned repulsive barrier, and we use a magnetic gradient to just give the atoms a little kick. And now some of the atoms tunnel through, others are reflected. And as they interact with the barrier, they're also interacting with this sideband. That means that we should have some hyperfine coupling. So now all we have to do is measure that precession angle. In the early experiments, we literally did a Stern-Gerlach measurement on the atoms. We applied a magnetic field gradient and separated two different spin states. Now we have other techniques for separating the F=2 and F=1 states, but obviously we know how to measure those populations. And here's an absorption image of two atom clouds. In this case, we had a clever trick my students came up with for turning off the barrier, but leaving the Raman coupling on. So all the atoms tunneled to the right. You see them on the right-hand side here, but we see some in the plus X state, some in the minus X state. We can look at that ratio and get a precession angle, which we think of as representing the time spent in the barrier region. And as a function of incident velocity, what we see is that the time spent in the barrier region scales as 1 over the velocity. So no great surprise, but a nice sanity check, and more importantly, a way to calibrate our interaction. We can repeat the experiment with a tunnel barrier. Now we see a cloud that's been transmitted, another cloud that's been reflected. We can again look at these ratios. And in the early data, we saw something that might seem very surprising. This time seems to grow as you lower the velocity. The dashed line here indicates the velocity that corresponds to the barrier height. Here it's about 5.1 millimeters per second. And remember, semi-classically, when you lower the incident velocity or lower the energy to U naught, you expect the time to diverge. So here we measure at finite time. First thing quantum mechanics does is suppress these unphysical infinities. But then you see something very strange. As you go to lower and lower velocities, the time turns around and actually starts to get smaller again. And this is something that we have to be a little bit careful about. These early data shouldn't be taken too literally. And the reason for that goes back to what Budeker actually realized in the 1980s. So remember, he picked up the Bas-Rybachenko idea and modified it. They were concerned about the effect of this magnetic field on the transmission characteristics. And hence they looked at a very small field. Budeker realized that wasn't quite good enough. So let's think again about what happens in this magnetic field. We have an X-polarized electron, let's say, coming towards a barrier. The Hamiltonian is diagonal in the Z basis. So really it makes more sense to think of that electron as a 50-50 superposition of up and down. And the up and down spins see slightly different potentials in the barrier region. And that, in fact, is what means that they'll pick up slightly different phase shifts. And the relative phase between up and down tells you the angle of the spin in the XY plane. So that really is what this Larmor time is trying to probe. And in that sense, it's not very different from the group delay, which also has to do with a phase difference or a phase derivative. It's not exactly the same, but they're closely related. The problem is the upspin aligned with the magnetic field sees a slightly lower barrier than the downspin, which is anti-aligned with the magnetic field. And of course, if you see a lower barrier, you are exponentially more likely to tunnel through the barrier. So when we look on the far side, we see more of these upspins than downspins. And when you add them coherently, that just means the total spin has both recessed about the z-axis and aligned a little bit with the z-axis, which seems weird because there's no torque in the xy plane. The torque was about z. But what's going on here is we're making a selection on the atoms. So S sub z or J sub z in total is conserved in this process, but more of the spin down are found on the left and more of the spin up are found on the right. What Büdeker recognized is that both the precession and this alignment effect are first order in the magnetic field. So even if you take the limit as b goes to 0, it doesn't change the fact that the total evolution of the spin is this three-dimensional evolution. So there's one component in the xy plane, sort of azimuthal angle, and there's this polar coordinate, the alignment angle. So there seem to be two different angles and therefore two different timescales. That seems mysterious, although it turns out there's other work, and Sokolovsky and Baskin are some of the pioneers of this work, which led to complex numbers. And when I say led to complex numbers, I mean they had a purely formal approach based on Feynman path integrals, no clear connection to any measurable quantities. But when you carried out their integral, since it was a Feynman integral over, the exponential of the action, you end up with complex numbers. And I think most people at the time dismissed this as having no real connection to reality. On the other hand, if you look at the real and the imaginary part of Sokolovsky's times, you find they correspond exactly to these two angles that Büdeker had. So there is some deep meaning to there being two different timescales that you can either combine into one complex number or not. Büdeker, looking at this picture, simply decreed that one should look at the full rotation angle in 3 dimensions. So add those 2 times in quadrature. It happened to agree with the times he and Landauer liked for other reasons. But more recently, we can unify all of these times by thinking about that weak measurement formalism that I described, this 1988 formalism of Aharonov, Albert, and Weidmann, which is really designed to post-selectively probe a system, and then look at what happens to the probe, to the measuring apparatus, if you look only at a particular final state for the system. And that formalism also leads to complex numbers, but since it's designed around a measurement protocol, it's very straightforward to interpret the meaning of the real and the imaginary parts of the weak value separately. The real part tells you what was the shift on the pointer, the needle of your measuring apparatus, the thing we thought we were trying to measure. And in this case, that corresponds to the precession of the spin. And the imaginary part tells you, quantum measurements have back action. You can't get away from that. And therefore, you end up with some effect on the momentum of your pointer, the conjugate variable to the pointer position. And in this case, the conjugate variable is the actual spin z component. So now that we know how to interpret these things, we go back and we try to do extraction of both of those angles on our atoms. That's a little more complicated because we can't just measure 2 populations. We need to do full quantum state tomography of the transmitted spin. So again, thanks to mostly Ramona and Shreyas, we learned how to carefully control all of these microwave phases and do measurements of SZ, SX, and SY independently. Remember, these aren't true spatial directions now. The up and down just correspond to the F equals 1 and F equals 2 clock states of rubidium. So we need to measure all the right coherent superpositions. But they did this beautifully, and we were able to look now at the full 3-dimensional spin as a function of the incident velocity. So if we begin with the green dots, which correspond to very high velocity that hardly see the barrier, and move towards red, where we see slower ones, we see the green dots, we began polarized along x. As you go to lower and lower velocity, you see more and more precession towards the y-axis. But eventually, at lower velocities, you see that you're dominated not by precession, but by alignment towards the minus z direction. And we can extract the 2 individual times. The plot gets very, very busy. There's also a lot of different theory here. These orange or salmon-colored dots represent the in-plane precession, the real part of this weak time, while the blue dots represent this back action, the imaginary part of the complex number. And you'll see that again, we see a finite time instead of this divergence you'd expect semi-classically or from the Büdker-Landauer time. A little harder to see whether or not we really get a turnaround here, although theory does predict one. And then for this imaginary part, you see that it's a purely quantum effect. You basically have to go below the barrier to get a significant imaginary time. David Spearings, now a postdoc at MIT, was able to greatly improve many, many aspects of this experiment and get two different data sets for two different barrier heights, go further below the barrier, lower the error bars, and see an unambiguous signature that if, for instance, you follow these red points, as you go beyond the barrier here at 4.7 millimeters per second, you begin to see the time very clearly decrease. And maybe more interestingly, if you sit here at an incident velocity of around 4 millimeters per second, and you lower the barrier height from the red situation, this 4.7 millimeter per second barrier, to the blue situation, the time goes up. So for a lower barrier, you actually end up spending more time inside the barrier. This is something that I call the red light effect. The idea is that if it's forbidden to cross the street, fewer people cross the street, but those who do, do so faster. The atoms seem to have a similar behavior. They know the region is forbidden. It suppresses the wave function inside the barrier, and they end up spending less time in the barrier. So far, this is confirming things that we had been able to predict. Theoretically, this is all, after all, single particle quantum mechanics. Well, single particle quantum mechanics plus an interaction with a probe, I should say. Leaving, however, some mysteries about how is it that the particles really spend so little time in the barrier? How should I think of the particle getting from one side to the other? And what we want to do next is actually develop an extended experiment that lets us look inside the barrier. And the idea here is if we could focus that probe down more tightly, we could have it only in this yellow region, for instance, measure how much time atoms spend just at the entrance to the barrier, move it a little deeper in, how much time do they spend in the middle of the barrier, how much time do they spend at the exit. And we're developing a few techniques that ought to let us make the barriers wider and the probes smaller and start doing this and looking into more clever ideas for using additional fields to maybe image even sub-wavelength. We don't currently have a working scheme for that. Anyone who has any great ideas, we'd love to talk about it. And finally, we're building an entirely new apparatus with Joseph Tawissen using potassium-39 instead of rubidium-87. It turns out, for purely technical, detailed atomic physics reasons, potassium makes it much more convenient to tune the interaction strength of the atoms. And we believe that by turning off any atomic interactions, we'll be able to make a much larger coherent cloud and then operate with larger barriers and be able to focus this probe in. We do, however, have very old theory predictions that date all the way back to my own PhD thesis for what we expect. And this is where there's a really interesting surprise. And that's why I'm driven to do the experiment in practice. We can imagine measuring the time spent in each region of the barrier. Here, for schematic purposes, we imagine a barrier going from -1 micron to +1 micron, just a rectangular barrier. And if you begin by thinking about reflected particles, they're indicated here in red. Well, almost all the particles are reflected. So asking where did the reflected particles spend their time, it's almost the same as asking where did the average particle spend its time. And that just means looking at psi of x squared. Just look at the square of the wave function. It decays exponentially. Particles spend a significant amount of time in the first exponential decay length and almost no time on the far side of the barrier. On the other hand, if you post-select on atoms which do get through the barrier, the situation becomes very symmetric mathematically, and it turns out you can prove they're equally likely to be found on the right-hand side of the barrier, near where they were detected, as on the left-hand side, where they were injected. It's related to the time reversibility of the Schrodinger equation at bottom. The interesting thing is the predictions are still built up out of the same exponential functions, a decaying and a rising exponential, meaning that we predict that the transmitted particles could be seen at the entrance, they could be seen at the exit, but they're almost never seen in the middle of the barrier. That remains very striking. It connects to this issue of how particles can tunnel in a time that seems to be faster than light. And we're still trying to figure out how best to think about that, but would really like to see it visually in the laboratory. Um, there are some complications, but I'm going to gloss over those if you forgive me. We, of course, wanted to compare transmission and reflection. One thing I left out here, if you simply look at the entire barrier, you're looking at the integral of these curves. And you may notice that the green curve is twice as low as the red curve, but it has two lobes instead of one. In fact, you can prove that for a symmetric barrier, the integrals are exactly the same for the two. And that's part of what drives us to do this more localized experiment. Just measuring the time does not allow us to distinguish between transmission and reflection in the end. Nevertheless, we thought we would test that experimentally. David Spearing spent a lot of time working on that. And he found something much more complicated. He instead found these curves where here we're looking at the local angular momentum along each three Cartesian axes, Sx, Sy, and Sz. And what we find is there are very complicated spin textures. The spin in the front of the wave packet and the back of the wave packet differ. And as we change the effective Larmor frequency here, that's indicated by color, the entire shape and even the sign of these things changes. It turns out this is all due to collisions between atoms. And we were working in a regime where we thought we could neglect interactions between atoms. It turns out in transmission, that was a really good approximation. We could do a simulation using the Schrodinger equation, non-interacting, or one using the Gross-Pittaevsky equation, including interactions. They agreed perfectly. But in reflection, that simply isn't true. Here are the Gross-Pittaevsky simulations. And as you see, they agree very nicely qualitatively with our observations. Um, it simply turns out that when you fire a particle into a barrier and let it be transmitted, you can easily reach a regime where the collisions are negligible. But once you look at the reflected particle, that's the particle that has to fight its way back through the rest of the incoming cloud. And it's much harder to get to a regime where interactions aren't important. Last year, we published, or no, by now 2 years ago, we published with Joseph Tawisan a PRL on this work because it turns out for detailed atomic physics reasons, it was controversial whether there should be any spin dependence in this reflection at all. We see experimentally that there is, but in fact, in rubidium, the interaction Hamiltonian is essentially spin independent. So it took some time to understand how it is that quantum interference and indistinguishability of the particles lead to this effective magnetic behavior. Finally, we want to see what is the effective measurement itself on the particles. So we're sitting here trying to observe particles while they're in a forbidden region. If we actually find a particle in the forbidden region, what's going to happen? This dates back to a question that Bill Phillips asked at a conference years ago. And I think, here's the schematic. If we have a wave packet tunneling and or being reflected through a particle, but we shine imaging light on the barrier, every now and then, a photon would scatter off of a particle inside the barrier, and we could image that on a screen. We could tell, oh, this atom is inside the barrier. And if we ever saw that photon on the screen, we would now know that the atom was inside the barrier region, which means we'd collapse it into a wave function localized in the barrier region, which must have more energy than the potential height, U naught. So we wouldn't be looking at tunneling anymore. And very interestingly, the mere act of seeing the particle there would give it enough energy to roll across the rest of the barrier. So our prediction was if you did anything that could tell with certainty that a particle was in the barrier, suddenly half of those particles would roll across the barrier, even if the barrier were a kilometer wide. So you could start with zero transmission, and imaging light near the entrance of the barrier would be enough to enhance the transmission across this barrier. So for years, we thought if we could find a way to do that, we would love to. We didn't have a great way of really measuring that. At first, we thought, well, we're using Larmor rotation to weakly measure where a particle is, give it a small spin precession. If we could increase that magnetic field so that it implemented a pi pulse on the atoms, really spin flipped any atom in that region, then that would definitely be a strong measurement. But that's not really a feasible thing to do in our situation. It took a long time before it occurred to us, what if we go ahead with a weak magnetic field as we're already doing? So we get a small, maybe a 10-degree rotation of the atomic spin. But then we only look for atoms whose spin points along the minus x direction. Remember, we began polarized along plus x. So if we look for minus x atoms, we see nothing. If there's a magnetic field here that rotates the spin by a little bit, then any particle that saw the field has some small but finite probability of appearing when we look for minus x. And we can only see particles that have interacted with the field. So it occurred to us that maybe if we just projected out only the minus x component of the final wave function, we'd be seeing atoms that had collapsed to be in the presence of this magnetic field. And I asked David to simulate this experiment fully and confirm that half of those minus x particles would be transmitted and half reflected so that we could go and do this experiment. However, that's not what he found. What I asked him to plot was the ratio of transmission to reflection just for the minus x spin as a function of where we put that magnetic field inside the barrier. And here on a semi-log plot is what he found. And what you see is it's not 50-50. This horizontal flat line, solid line, indicates a ratio of 1. That's what we expected. Instead, he finds slope lines, so exponential dependence on position, that say very interestingly, if you find the particle in the barrier using this magnetic field, it's exponentially more likely to tunnel out on the side it's closer to. If I probe for the particle on the left, most particles leak out to the left. But if I probe on the right, most particles leak out on the right. And the slope here is just given by the exponential decay constant. This ratio turns out to just be e to the 4 kappa x. And you could prove that after the fact pretty simply. It's very easy to understand why we did not see my original expectation. It's because we're interacting with a time-independent magnetic field. That time-independent interaction cannot change the energy of the particle. So there's no way that this will collapse the particle into this higher energy wave packet. On the other hand, it looks like we are getting information about where the particle is. And this is something that was surprising to me. The particle behaves as though it starts wherever my probe was. So I know where it is inside the forbidden region. And yet it has this exponential dependence on distance to the edge of the barrier, meaning that the particle does not have enough energy to be in the barrier, and yet I know where it is in the barrier. So that already is something that we'd like to confirm. But we realize that to truly collapse the particle, you don't want to measure, was the particle ever in the barrier at some point in the past? You need to measure, is the particle in the barrier now? So you need a time-dependent potential. And never mind the calculation. When David added time dependence, so he pulsed that probe on and off, he found that for the time independent probe, we got this blue curve, that exponential. But as you went faster and faster, you evolved towards this green curve, where indeed you see essentially a 50-50 ratio, no matter where you put the probe inside the barrier. So this is what we'd like to do experimentally. The open question for us was, how fast does the probe need to be? How quickly do you need to probe a particle to be sure that it's still inside the barrier region? We have theory about that, but we don't really have any interpretation for it. We're still trying to figure out what it means. What we thought early on is that if that time depends on where you are in the barrier, which it seems to, then we have a position-dependent time. Maybe we've identified a characteristic timescale for leaking out of a barrier. Or maybe it's not a velocity scale, maybe it's a diffusion constant or something like that. Instead, it turns out to be neither. The time it takes to leak out of the barrier, as evidenced by this kind of measurement, scales as the square root of the distance to the edge of the barrier. And that was entirely unexpected, but it sort of falls out of perturbation theory and our numerical simulations. And we'd like to confirm it, but we'd also like to understand really what that means. All right. I think I spent longer talking about these atomic physics experiments than I meant to. So I don't want to keep you very long. I think what I'll try to do is just abbreviate the other experiment that I'm talking about. A lot of this has already been published, and I'm happy to answer questions about it later. But I'll try to give the short version in the next 10 or 15 minutes about this secondary experiment. So the previous experiment, I was telling you how much time Adam spent in this tunnel barrier, in this light beam. And it turns out that now we found ourselves asking the opposite question, asking how long photons spend inside atoms. And really, this grew out of a series of experiments where we were trying to develop nonlinear optical switches that work at the single photon level, a much more applied mindset, thinking about doing quantum non-demolition in order to build quantum logic gates and things like that, thinking about the quantum computing. And for those of you interested in that, here's the long series of papers that led up to it. But deep down, we're foundations of quantum mechanics people. We wandered into something we didn't understand, and we got motivated to continue that work. The question, the way we think about it now, is to say that we all know when light traverses a dielectric, a piece of glass, or an atom cloud, it slows down. But photons themselves we think of as traveling at the speed of light. How should we think about the photon spending its time? And one picture that some people like to give to students but don't usually take too seriously is that even if the light is going through a piece of glass far off resonance, there's always some possibility of a virtual excitation of the atoms or molecules in the glass. Even if it's very far detuned, you can violate energy conservation for a short time. That's one hand-wavy interpretation of the energy time uncertainty principle, meaning that some of the atoms spend time in the excited state before releasing the photon and letting it go on its way. And you can think of that as being what slows the light down. Now, that's not entirely crazy. If you look at the index of refraction around a Lorentz line, you find that far from resonance, it drops off as 1 over the detuning, 1 over the energy deficit, so to speak, which agrees with the simple Heisenberg picture that delta T is something like h bar over delta E. Now, of course, on resonance, we don't expect that to work because on resonance, well, n goes back to 1 and 1 over delta diverges, but obviously you don't need an uncertainty principle argument if you have the right energy. So you might just think the whole picture breaks down. As an atomic physicist, I kind of thought maybe you have this diverging delay, but then it saturates when it's on the order of the atomic lifetime, something like that. In fact, the situation is even more complicated than this looks because the delay time for the photon is not just given by n, the phase velocity, but the group velocity. And it's well known, go back to Sommerfeld and Briand, that on resonance, the group velocity becomes negative. So this so-called delay time becomes an advance, a negative number. And it's very hard to understand where the photon is spending its time by thinking of it being, slowed down in the atoms. So Josiah Sinclair, who was really the guy who had a lot of these realizations and pushed to do this experiment, we decided to just measure on resonance how much time do atoms spend in an excited state if the photon is transmitted, kind of like in that tunneling experiment. And there's something we realized we could do rigorously, and it's so simple it keeps seeming to me like it should be in lots of textbooks, but I've never actually been able to find it written anywhere. Forget about the post-selection. Just imagine sending, let's say, 1 photon into a cloud of atoms. The photon has some beam area A, the cloud of atoms have some absorption cross-section sigma, and are deep enough to give me some absorption. They have some optical density. Well, it turns out that at any given time, the probability of any of the atoms being in the excited state is just given by the intensity of the the intensity of the light divided by I sat, which means the number of photons per absorption cross-section per atomic lifetime, roughly speaking. On the other hand, the probability of a photon being scattered is just the number of photons per cross-section, or the probability of the photon being within that cross-section. So these two formulas are very similar. They differ only by this atomic lifetime. And it turns out that that means if you define how long did atoms spend in the excited state by just integrating the excitation probability over all time, you find an excitation time that's just equal to the absorption probability multiplied by the spontaneous lifetime of the atoms. Really simple formula that leads very naturally to one simple interpretation, which would be the following. On resonance, some fraction of photons are absorbed. They hit an atom, excite the atom spontaneously decays, and the photon is lost to the size. The rest of the rest of the photons somehow get lucky. They miss all the atoms. They sail on through without ever exciting an atom. And that way, if you look at the average time, you see, well, every scattered photon, absorbed photon, led to one spontaneous lifetime in the excited state. All the others led to zero, and that gives you the formula here in red. But this is a very interesting prediction because it suggests, wait, did I write that down here? I have too many things floating on my window. Yeah, it suggests now that if you look only at the case of transmitted photons, you will find no atomic excitation. So this is what we wanted to probe. We probed it with a effectively two-level atom. And the idea is that as you send in a photon, if it's absorbed, it moves the atom into the excited state, reducing the phase shift that would be seen by a probe. So if we had some additional beam probing the atoms, it sees some Lorentz profile phase shift, index of refraction. But if you reduce the number of atoms in the ground state, you reduce that phase shift. And that's an example of the Kerr nonlinearity, a chi3 nonlinearity that can make two light beams interact with one another. And our question was, does that Kerr nonlinearity only work for photons that are actually absorbed? If you post-select on the pump photon having gotten through the sample, does that mean it has zero effect on the probe light? That's what Josiah and I convinced ourselves of. We asked some other people, and some actually made the opposite prediction. They said, no, no, no. The absorbed photons were all absorbed in that first decay length, where the OD was on the order of 1. But a transmitted photon must have traveled through the entire cloud, no matter how high the optical density is. And it was polarizing atoms throughout that whole cloud. So, in fact, you should see a greater excitation for the transmitted photons, not for the absorbed photons. Well, we built the experiment. We tried to send in one pump photon at a time. In the end, we weren't able to do exactly that. We had to play some roundabout tricks, but I won't go into that in too much detail. And we simultaneously sent a probe beam through that allowed us to make a phase measurement. And the idea is the longer the atoms spend in the excited state, the less phase shift the probe will pick up. However, we have single photon detectors, so we can directly check whether the pump photon was transmitted or not. And we can condition that phase measurement on whether or not we see a transmitted photon. So in fact, what we end up doing is looking at the difference between the phase measurement when the photon is transmitted and the phase measurement when the photon got scattered out of the beam. This is what the whole setup looks like. We use a magneto-optic trap of rubidium-85 in this case for no particular reason. We send in signal pulses that are on the order of a single photon, but really dozens of photons in this case. We check whether or not the photons are transmitted, and simultaneously, we do a phase measurement on a counter-propagating probe beam that has an additional frequency component to let us do that difference. This, again, was a really heroic experiment. We're looking for phase shifts on the order of 10 microradians as these beams that are relatively weak go through all sorts of classical noise and a big breathing cloud. It took billions of pulses to do this. My students slept for very few hours out of 1,000 hours of real time. And this is what the data look like for the kind of classical level effect. When I say classical, I mean each of our 20 nanosecond pulses had about 34 photons, which made it relatively easy after averaging, 100 million times to see this almost milliradian phase shift. And we did it for two different detunings just to sanity check and confirm we were seeing what we thought we were looking at. When we look at the effect of a single photon, which we do by taking these differences, that becomes extremely hard to observe, and only because we already have a well-calibrated pulse shape from the classical measurement are we able to do that. You see over here, we have some smoothly varying noise that's fitted in green, but in every one of these cases, there's an excess phase shift in that shaded region that corresponds to the nonlinearity. So either for 34 photon pulses or for 134 photon pulses, we see this systematic shift. We see that it follows the right detuning dependence. And statistically, we were able to really extract good information. That's one data point here. We had one incident OD, one incident pulse shape, and we found that the phase shift for transmitted photons, what we call phi t, was about 75 or 80% as large as the mean phase shift for non-post-selected photons. Remember, we expected zero. So we really worked very hard to check all the systematic effects and convince ourselves that our theory was wrong, which left us trying to understand why this phase shift. And on this plot, there are many different models that we tried. And you see, all we could really tell at this point was it disagreed with zero. There was no very good model to explain what this number was. Turns out there was no prediction in the literature for what you should see as a nonlinear phase shift when you post-select only on transmitted photons. We did eventually understand one rather basic thing that perhaps should have been obvious sooner. Um, Remember, we have this weighted average. We know the average excitation time if you don't post-select is the loss probability times the spontaneous lifetime. So if we take the transmission probability times the time for transmitted photons, add the loss probability times the time for lost photons, we should get this. However, when we find that the time for transmitted photons is greater than zero, that indicates that the time for lost photons must be less than the spontaneous lifetime. So the corollary of our measurement is that when the photon is absorbed by an atom that then emits the photon to the side, on average, that photon spends less than a lifetime in the atom. And that led us to wonder why. And we realized in our regime, with a relatively high OD and very short pulses on the scale of the natural line width, the pulse propagating through the medium gets distorted. It picks up a phase flip, kind of looking like a zero area soliton. And if your pulse has a phase flip, then the first part of the pulse drives the atom up in excitation, up the Rabi sphere, the Bloch sphere, sorry. And the second part pulls it back down coherently. So there's clearly a coherent forward emission that we should have anticipated. That means you can have photons emitted in the forward direction, which did spend some of their time in the excited state. And that emission process also explains why the atoms that emit to the side spend less than one spontaneous lifetime in the excited state. That's a nice hand waving picture. We tried to use that to really come up with a rigorous timescale for the excitation, but you cannot, because no semi-classical model can describe what happens when one photon goes one place or another. That's simply beyond the scope of any semi-classical theory. We needed a full quantum treatment of this dissipative open system with post-selection. And it turns out that's kind of state of the art for calculating quantum open trajectories. We teamed up with one of the experts on this, Howard Wiseman in Australia, who helped us develop this model that indeed showed us that we'd get a positive time for very large ODs that would drop down towards zero for smaller ODs. We thought life would get simpler if instead of having these short pulses with all that distortion, we went to the CW, continuous wave limit, very narrow band pulse. And instead, what we found is if you go to the narrow band limit shown in these other colors, here's a 50 nanosecond RMS pulse, you actually get negative times. And at first, we just thought that was an error. What does a negative time mean? Little by little, we realized it just means a negative phase shift. It is physically possible in our system and is, in fact, analogous to many other seemingly paradoxical behaviors with weak measurements. The interesting thing to me was that the slope of this curve in the CW limit was exactly minus the spontaneous lifetime of the atom. In other words, the time spent seemed to be minus the OD times the spontaneous lifetime. And that's a familiar expression. For people who study optical pulse propagation, we immediately recognize that is the group delay. Remember, the group velocity on resonance is negative. So this time we're finding is just thickness of the medium divided by that negative group velocity. A time that we knew described the propagation of the peak of a pulse, but which we never thought would describe the time spent in an excited state. What does it mean to spend a negative amount of time in the excited state? Well, what it means operationally is just that the phase shift written on a probe flip side. And that was our prediction with Howard. It was recently published in APL Quantum. Kyle Thompson was the first author on that. And Daniela Angulo managed to do the experiment. We're very excited to see this confirmed. As we vary the duration of the pulse, we see that for very short pulses with these complicated dynamics, we get positive excitation times. But as we go towards longer pulses, essentially narrow band on resonance continuous wave, we see negative times. And the agreement is pretty good for a number of different optical densities and RMS durations. So this is on the archive. It has been for a year, more than a year. We're still trying to convince referees that we know what we're talking about, but trust me, we do. And finally, I don't think I'll describe this experiment to you, but I'll say it raised an interesting question, and it was my student Andy Zhao who really got hypnotized by this. We detect our photons with on the order of nanosecond resolution, which is much less than the natural lifetime or the pulse duration. And you can ask yourself, in these CW experiments, we send in a long pulse where we know the exact frequency of our photons, but then we see the photon at t equals 0. We know exactly when the photon landed. How should we think about the intensity of that pulse? Was it really localized to the moment at which we detected it? And that's really interesting because you can ask yourself if you simultaneously get the benefit of knowing the frequency of the incident pulse and knowing the exact time of arrival of the photon. It seems to fly in the face of the uncertainty principle. But in Andy's experiment, we actually confirmed that you can get phase shifts here due to these detected photons that are much larger than the phase shift you would expect for such a long pulse. So it seems in some way as though you can simultaneously get an advantage from knowing the frequency of the incident pulse and knowing the time of arrival of the photon. We're still trying to figure out how best to describe that, and we're writing up a paper that has not yet even been posted to the archive, but keep your eyes peeled because I think there are some really interesting questions here, and hopefully those will be up on the archive soon. So in summary, I told you about two different kinds of experiments that try to probe the history of quantum systems. In one, we showed that we really could measure how long atoms spend in a barrier region, but we're hoping very soon to even probe where they spend that time and what the effect of measurement is, how measurement can enhance transmission, and how quickly you need to do a measurement to really know that you're studying the present state of affairs. And we've shown both theoretically and experimentally that the time single photons spend as atomic excitations is exactly the extra propagation time you expect from the group velocity, even when the group velocity is negative. And I'll mention that's related to some other funny effects that Near Davidson and Bob Boyd have observed recently in a phenomenon known as the transverse piezo drag effect, something I'd never heard of until about 3 years ago, but it's really an amazing experiment. And finally, we're now studying this question of what does it mean to prepare a photon of a given frequency, but then find it at a given time. So with that, I'll thank you all for your patience. I know I've been rambling on and open it up to questions.
Thank you, Ephraim, for positive time spent for explaining beautiful effects. And yeah, very fascinating. So we are open for questions.
May I ask a question?
Yes, please, Alexander Korchin.
Okay. Yes, Alexander Korchin. So when you're discussing time of delay, in standard scattering theory, you calculate time delay by just taking phase shift of scattering phase shift, calculate derivative of energy, and you will get a time of delay in any potential.
Yes.
So if you apply this approach, will you get the same of the order of magnitude, the same time of delay?
Yes. So in fact, I mentioned that in the tunneling case, Wigner was one of the first people to look into this. Actually, Nicole did some of this work even in the 30s. But that approach was precisely this. It's a little tricky because there are two energy scales. So it turns out if you look at the transmission phase and you take the derivative with respect to incident energy, that is what we mean by the group velocity or the group delay, and that's been experimentally confirmed. If instead you take the derivative with respect to the height of the potential, that gives you a different time scale, and that turns out to be the Larmor time. And in the regime we're in, it doesn't matter which energy you change, those two derivatives are almost exactly equal. But yeah, that's kind of exactly what's going on. And in scattering theory, especially in nuclear physics, I think the Wigner time is very well known for the scattering into another channel. So in fact, when we talk about these photons exciting atoms and either being transmitted or being scattered to the side, the time you expect for a photon scattered to the side is this other derivative that turns out to be just 2 divided by the full width half max of the resonance. And that's what people usually call the Wigner time. Antoine Boyer, about 10 years ago, verified that prediction for single atoms in his atom tweezers. And the experiment that my student Kyle is now trying to do is precisely to look not at the transmitted photons, but at the scattered photons. For us, the thing is, we're not trying to measure the delay time for the photon. That's kind of well understood. We wanted to measure how much time the atoms spend in the excited state. And we didn't realize those 2 things were guaranteed to be equal. And that's what we found here, that even if you measure the atomic excitation time, you get that same quantity.
Okay, thank you. Thank you.
Thanks for the question.
The next question by Denis Bondar.
Fantastic, Tom. I wanted to ask some clarifications. So in the when you make a Raman beam, right, you would need 2 beams. But did I understood you correctly that in that experiment you actually have 1 beam, but you modulate it also with like 6 gigahertz, right? So
That's right. So we have the barrier beam and then one sideband 6.8 gigahertz away. Exactly.
So do you shake the barrier, or you actually like how does it actually how is it implemented, or it's a separate beam of the same frequency which you actually oscillate?
So we take our barrier beam and we send it through an electro-optic modulator that phase modulates the beam. That generates 2 sidebands, or even more than 2 sidebands. And because the 2 sidebands have opposite phases, the Raman transitions would cancel out. So we then send that through a Fabry-Perot that's tuned to remove the undesired sideband and just leave us the 2. So it's not a physical shaking, it's a phase modulation and then this other thing. In the new version of the experiment, we're going to change that. We're now trying to better focus the barrier, and instead of just using the barrier as a probe, we'll have this second beam come in from the other side so that we can actually translate it and try to get spatial resolution.
Which corresponds to what you were showing in the slides, basically, like schematically.
That's right.
So one more question. In this Bütikofer-Landau picture of that, I thought the initial condition was that the particle was spin polarized. And then
Yes.
you had this like in the middle of your talk that it sort of equals to spin up plus spin down. I didn't quite understand that aspect.
Sorry. The particle is spin polarized, but orthogonal to the applied magnetic field. So in their case, they or Bütikofer described the magnetic field along Z and the spin polarized electron polarized along X so that it could precess about the magnetic field.
Mm.
Right, it's not spin polarized along the field, or there wouldn't be any precession.
But in your case, you have like a little bit of sorry, but then why do you have this? Is this happening only under the barrier where you have spin effect start shifting? So not spin effect, but the magnetic.
Exactly. You turn the magnetic field off everywhere except in the barrier, and that way you say that the Larmor precession is measuring the amount of time spent in the barrier region. And it turns out that, although that seemed like such an uncontroversial thing that no one complained about that definition, it is exactly equivalent to what Aharonov's group defined a few years later as a weak measurement. Oops. Someone, I think, has both a speaker and a microphone on. We're getting some echo effects.
Hello,
Konstantin Bloch.
Question, may I ask?
Hello. Ephraim, thank you. Fantastic talk, very interesting. I have one remark and one question. So first, concerning the Wigner time delay, I think it also has a natural complexification. So complex form with real and imaginary parts, because if you take phase gradient as a gradient of logarithm of transmission coefficient, it has imaginary and real part. And it has been described and very recently measured by Stefan Lage last year, PRL, that the real part is just the usual Wigner time delay, and the imaginary part corresponds to the shift in the conjugate variable, which is frequency of the transmitted wave packet. So if you calculate the expectation value of frequency, it's also shifted proportionally to the imaginary part of this Wigner time delay. So this is a remark.
Thank you. Certainly, in our weak value stuff, that's exactly how the complexification works.
Exactly.
It's that logarithmic derivative. But I hadn't seen it for the Wigner time, and I don't know this on-logger work. So thank you very much. I'm going to look that up.
Sure. And second question, when you considered spin precession, did you or somebody considered an option to deal with optical spin, which is polarization, and magneto-optical resonator? So if you have magneto-optical resonator and precession of polarization for the wave packet passing through this resonator.
Yes and no. There have certainly been people who try to do the optical version of this Larmor clock measurement. I don't know of any that used magneto-optics. There was a group, I believe that it was Deutsch and Golub in Israel, who used liquid crystals or pneumatic fluids of some sort inside the gap between two prisms for frustrated total internal reflection. And as you imagine, it's mathematically the same thing. So they found very closely related results. That's exactly right.
Okay, thank you. Thank you very much.
Thanks for the question and the comment.
So Konstantin Lukin would like to ask a question. Andrei,
Yes, but please maybe turn off speakers because we hear the echo.
Oh, that's very soothing, actually.
Yeah.
The time scale is perfect.
The point is that just a second. No revelation.
Yeah, I never know how to get around that. You can disconnect audio entirely, but then I won't hear you either.
Okay, now right.
I hear you, but still with an echo. I'll do my best to follow. Go ahead. I know now you're muted. Could also type into the chat if that's easier. I should be able to see if you can type your question into the chat. But right now your microphone is on. Now you're back.
One speaker. Microphone, I don't know.
No, it was all right. We heard you.
Off the microphone. Sorry.
No, we all go through this. Can you just turn the volume down to 0? Because your microphone is working now. It's just that the speaker is also playing.
I don't know what kind of reverberation. What is so.
Konstantin Alexandrovich, maybe you can type your question.
So I suggest I switch off and then switch on, and you continue discussion. And I will later on. Okay.
All right.
Yeah. Please, Sergey.
Yes, thanks a lot for the very inspiring and beautiful work and presentation. Of course, for me, in particular, the values were also astonishing that the quantum barrier is micrometer size, and the particle can spend their microseconds.
Milliseconds, yeah, they're going a millimeter a second. So.
Yes. Can you tell more about the pump probe measurement? And I'm more interested in the model they used to describe it. Which of the values for the signals is the probe signal considered weak?
So yes, let me try to go back a little bit here if I can. Oops. Sorry, do you still see my slides? I'm no longer sure what I did.
No, you canceled sharing.
Right. I didn't try to, it just happened. Okay. I think we're continue to share this. Okay, I have no idea what that means. Let me see what I can tell you about some of the experimental details. In the original version here, as I said, we had pulses about 20 nanoseconds, focused to about 20 microns within our kind of 1 millimeter cloud. The light is at 780 nanometers. That's the 5S 5P resonance of rubidium. And typically, we had tens of photons per 20 nanosecond pulse. The probe was actually resonant with the same transition, but in a matching telescope, counterpropagating. And I'm trying to remember, it was slightly more intense. I think it typically had a few hundred photons per 20 nanosecond period. In order to measure the phase, we use a kind of frequency domain interferometry. So the probe actually has two different frequency components. And the idea is that one of them is detuned by about one line width from resonance. So it picks up a big phase shift that depends on that signal photon. And the other one is detuned by 100 megahertz. And it's just there as a reference. It's mostly not interacting with the atoms. So that's kind of the experimental setup. The theoretical model is greatly simplified. The theoretical model imagines a single excitation. So a single photon incident in some pulse. And we treat it not really even in a second quantized theory, but as a sort of wave function for the excitation. And the idea is that inside the atomic medium, at each point in time, the excitation could either be a photon or it could be an atomic excitation. So we use an extension of just, the optical block equations to model the coupling between the photon field and the atomic excitation field. But we're really just doing the quantum mechanics of a single excitation propagating through that medium. The thing that complicates it is that the atomic excitation can also decay to the side to channels that we're not observing, which you have to treat as a non-unitary evolution. And that's where Howard's formalism really came in. He has been studying problems like this and understood the right way to renormalize the wave function at each instant to properly treat this. Essentially, what we understood before that came out of this Aharonov formalism is that trying to see. Unfortunately, I'm not doing this on something where I can easily write, so I'll be drawing castles in the sky. If you want to know the value of some observable for a particle that's prepared in initial state I and later found in final state F, in our case, the observable is just the projection operator onto excited atoms. We want to measure, is there an excited atom or not? You can calculate that by taking the matrix element of that observable between I and F, and then dividing by the overlap between I and F, the inner product of I and F. So for unitary systems, that's a well-known formalism, and we all know how to do it. The problem here is, since we end up with these non-normalized wave functions once there's absorption, we needed to know exactly what function should we use for the final state and the initial state. And that's what Howard helped us do. Basically, we end up with something that looks like a renormalized optical block equation that takes this initial wave packet, lets it become a sort of spinner with an atomic excitation component and a field excitation, and then propagate all the way through, and then do the reverse and look at a transmitted wave packet and propagate it backwards in time to see what the intermediate time wave function that corresponds to. So at each time, if we want to know what's the atomic excitation probability at this time, given that we're going to see the photon transmitted later, we need to have this incoming wave function psi I that we already knew how to calculate, and this backward propagated wave function psi F that was much trickier, and that was Howard's real contribution. And then we just used the Aharonov formula. So again, this, where is the paper? It's a few slides down. Sorry, just have too many Zoom controls and keynote controls floating on top of my screen. But one of these slides should give you the theory reference. It was this, APL Quantum, just came out last year, I think in November even, or December. All the details are in that paper.
Thanks a lot.
So now, Konstantin Lukin, I removed reverberation.
Fingers crossed.
Yeah, I was so eager to connect properly that I did it 2 times in different computers. Sorry, but thank you very much for the excellent results and the pictures and theory. And my general question is that related to photon measurements with photon, that when you do these measurements, so you, as I understood, they consider the quantum mechanical picture of absorptions and the propagation through the medium of this photon without interaction. But there is also could take place a classical phenomenon like polarization. Someone already mentioned today in questions, and there is. I think for so fine measurements, so accurate measurements, it's necessary to ensure that the classical and quantum pictures cannot be realized simultaneously. How to separate them? Because why it question? Because there is a dipole, the classical model of an atom, even the simple atom, hydrogen, atomic hydrogen, that the magnetic and electric pulse, it could be modeled, they're mechanically tied. And then interaction of electromagnetic magnetic and electric field of photon will interact this with this momentum, magnetic and quantum momentum. And then this affects the propagation. That is why the question appeared. Your experiment, your theory, did you care about this splitting the area of quantum phenomenon and classical phenomenon?
Well, certainly it's always on our mind, and if we had something that already disagreed with the classical physics, we'd be disturbed, because for the pump photon itself, we're looking at linear propagation, right? The classical theory should work fine. But the way that they get reconciled, I think here is the following, that we can certainly calculate the sort of time-dependent energy density in the atomic excitations semi-classically, meaning we treat the atoms quantum mechanically, of course, but we treat the field classically. And we get an answer for that. But the experiment that we're doing is looking at correlations. We're looking at this excitation, or looking at the phase shift on our probe beam, and correlating that with whether or not a different detector goes click. The classical theory is incapable of correctly describing those correlations, which really have to do with the entanglement between two different beams. So if we don't do the correlation, we just look overall at the phase shift on the probe, the classical theory is perfect, but all it tells us is the mean time spent in the excited state is the scattering probability times the lifetime. And it doesn't tell us how to divide that into cases where this photon is actually transmitted or is actually scattered. There is no classical meaning to that statement. So it's not even a testable question for the classical theory. And when we do both, they're completely consistent with one another. It's just that one goes beyond the mean values to these correlations that are a purely quantum question.
I mean, no, I agree with you what you said, but I meant that the mechanism of interaction of photon with media You talking about in terms of absorption, some photons, other photons, not absorptions, and then I meant exactly this, the just beginning of what kind of mechanism could provide the delay or retardation or this point, not final calculation.
So certainly this language of saying, some photons are absorbed and others aren't, people do tell me to be cautious about that. Obviously, the correct treatment is that there's a polarized sample with some coherent superposition of ground and excited states. They do decohere because of the spontaneous emission. So it would be interesting to revisit this in the far detuned limit, where all the excitation is virtual, and you want to think of it as purely a coherent process. But I'm not even entirely sure what I can say about that. When we do the full modeling, as I was describing that paper with Howard, we certainly don't make any assumptions about splitting it into absorbed and not absorbed. We just try to do the full quantum treatment of the coherent state that this excitation can be in. But I think exactly how to think about it is exactly the problem for us. And that's why our initial intuition was that every time a photon is really absorbed, it ends up being lost due to spontaneous emission. And that obviously was oversimplified and neglected the coherent processes that occur. There is a way we can even understand these negative times by using a sort of semi-classical picture of interference between the different contributions. You can say that there is, let's say, a Feynman path corresponding to no phase shift because the photon was never absorbed, a Feynman path corresponding to a phase shift because the photon was absorbed, and they're Feynman paths. They're not real physical processes. You have to add them coherently. But it turns out when you go through that calculation, if you add them coherently, they add 180 degrees out of phase. And that phase shift is what makes it look like the resulting time or phase shift is in fact negative. And in the same theory paper, we try to go through some of those models. But I think it's far from being crystal clear right now. The best way to think about these things may yet need to be developed.
Okay, thank you very much. Thank you. I agree.
Well, thanks for the difficult question.
Yes, thanks also for interesting answers, not only questions during this session, and thanks for the interests of all participants, and thanks again for a beautiful talk.
Well, thanks again for having me, and thank you all for your attention. Have a good evening, and all my best wishes. And I look forward to interacting more with some of you in the future, I hope.
Okay. Thank you very much. Thank you.
Yes, please, Sergey, announcement that the next seminar.
Yes, the next seminar will hopefully be in a week, not in 2 weeks as usual.
Yes.
Thanks. Bye-bye.
Thank you.
Bye-bye.
Bye.